All right, so today we're going to go over a spec cipher. I'm going to do a deep dive on that. So all my information came from Wikipedia today. We trust Wikipedia on Barathelos coding. Okay, so what is a block cipher? So a block cipher, you're given a text of data and you access that data with a key, right? And so you scramble that data and you access that scrambled data with two words, and a word is a block of data, like not just like a hey hello type word, but a word of data, a chunk of data. And it has two words, the key and then what the key is accessing, right? So a key can be 12, 24, 36, any divisibility by 12. It can be, and so a key controls the scrambling, right? And the same key has the same output. And the cipher applies the same transformations, the same transformations a bunch of times to make it secure. So it keeps uh, scrambling it, right? And so if you have that key and you have that scrambled thing, and you know how many times it's scrambled, you can reverse it to decrypt the data, right? And so um, yeah, I mean, again, fixed size blocks, yeah, whatever. So what is SPECK? SPECK was released in 2013 by the NSA. We don't trust the NSA, but like, fuck them, whatever, I guess. Cipher type ARX, and it's for Internet of Things. So for my case, I'm using it on software-defined radios, but SPECK is a lightweight cipher designed to encrypt data on low IoT devices where traditional ciphers are too slow or large. So Spec is optimized for software, runs fast on general CPUs. It's good for like Pi's and other microcontrollers. It's pretty simple. Simon is optimized for hardware. It's efficient in logic gates. It's a slightly different design philosophy. So the building blocks of Spec. So spec uses three simple operations, and that's literally it. So you have the modular addition, so you add two numbers together, and it overflows the size and wraps around. So it does mod arithmetic. So like the example you have here, the odometer, your car, right? You have 999,000 miles, and then you get one more mile, it rolls back to zero. So rotate is the bit rotation. So you shift all the bits right or left. In my current project, we're shifting it right, I believe, and then the one that goes on to the end starts back at the start. So let's say you have a list of bits and it's like 1 through 4. So then one would go to two, two goes to three, three goes to four, four goes to one. XOR, it's comparing the bits. So if they're the same, then it's zero. If they're different, it's one, basic stuff. It mixes the key into the data and it's perfect for encryption. Yeah, no lookup tables. It's good against caching, all that stuff. Okay, so round function, how does one round work? You rotate x by 8 bits, then you add the x plus y mod 2 to the power of, what is it called? 2 to the power of 8. In my case, I think it's the it's subtracting by 8, I think, in my personal code. What I'm doing, I think it's based off the words bits, but uh, XOR X with a round key K, then you rotate left Y by 3 bits, and then XOR Y with new Y. So uh, X and Y are two halves of your data block, and then the round function scrambles them together with the key, and then after like you just keep doing it however many times, the output becomes hard to read. So yeah, the block sizes and the key sizes, yeah, you know, the two words, and then these are the um, the corresponding amount of rounds and use cases. Um, they have pros and cons, so it kind of goes into the throughput, but yeah. Key schedule generating keys. So you have one approach where you can do it once and then caching it, or you have the you can do it on each iteration. So the iteration is probably better in terms of your RAM usage, just because you're just not storing the data on the RAM, right? You're not like caching the data. but it slows down the output. While the traditional approach, while you cache it, and you have fast, I guess, fast lookup for the keys, it's um it's not as effective on like smaller microcontrollers. So the traditional approach, you run a key schedule once before encrypting, and then you store it in RAM, and then you look it up during encryption. And then after you're done using it, you can discard it and then generate a new one. While the spec, like the this approach is you just keep computing it. Okay, so these are the performance. Yeah, cool. And then ARM versus AES architecture, just the CPU cores. Yeah, spec in the real world. These are different uses of spec. So smart sensors, thermostats, wearables, when they're using secure telemetry data, satellite systems like RF stuff. That's what I'm doing it for. So these are just some cool security. There hasn't been any successful attacks on a full round spec, so it's pretty safe. Um, best attack only reaches 72% and is barely faster than brute force, so that's pretty good. A round counter, it's built in the key schedule. I mean, although it's like safe, like internationally, I know that Japan and Italy don't want to implement like on a global scale. It's not being implemented as a standard because people are scared of the NSF having a backdoor, which they definitely do. Um, so, I mean, it seems safe enough for me, so we're cool with it. Yeah, I see it's here. Yeah. Um, Germany, Japan, Israel blocked it to get it standardized. Yeah, they have some weakness. Um, they don't trust it in terms of on Linux, which is open source. So if Linus doesn't trust it, maybe you shouldn't. Um, but it is standard for the US and for the national level. So I mean, it seems clear. I mean, until someone proves it wrong, it's pretty safe. Okay, so SPEC versus AES. SPEC was designed by the NSA, and AES is designed by these two guys. It's ARX versus substitution permutation in terms of like how the structure is. The speed on ARM CPU is 5 CPB versus 15 to 20, so SPEC is pretty fast. It's pretty small, while AES is much larger. Minimal RAM utilization while high RAM, and you guys can read. The only thing is just the trust and integration onto physical devices. So these are the key takeaways. SPEC is a lightweight block cipher made by the NSA for IoT and hardware constrained devices. It only uses 3 operations, so it's pretty simple to implement. The round function doubles as a key scheduler. SPEC is very fast on ARM devices and is 3 times faster than AES without hardware acceleration. And there's no tax that's broken the full cipher, so pretty W.